The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so we were looking at vector fields, and last time we saw that if a vector field happens to be a gradient field, then the line integral can be computed actually by taking the change in value of a potential between the endpoint and the starting point of a curve. Okay, so if we have a curve C from a point P0 to a point P1, then the line integral for work depends only on the endpoints and not on the actual path we choose. So we say that the line integral is path independent. Okay, and we also said that the vector field is conservative because of conservation of energy, which tells you if you start at a point and you come back to the same point, then you haven't gotten any work out of that force. So if we have a closed curve, then the line integral for work is just 0. And basically, we say that these properties are equivalent, being a gradient field or being path independent or being conservative. And what I promised to you is that today we would see a criterion to decide whether a vector field is a gradient field or not, and how to find the potential function if it is a gradient field. Okay, so that's the topic for today. So the question is testing whether a given vector field, let's say M and N components, is a gradient field. So for that, well, let's start with an observation. Okay, so say that it is a gradient field. So that means that the first component of the field is just the partial of f with respect to the variable x. And the second component is the partial of f with respect to y. And now we have seen an interesting property of the second partial derivatives of a function, which is if you take the partial derivative first with respect to x, then with respect to y, or first with respect to y, then with respect to x, you get the same thing. So we know f sub xy equals f sub yx, and that means m sub y equals n sub x. Okay, so if you have a gradient field, then it should have this property. You take the y component, take the derivative with respect to x, take the x component, differentiate with respect to y, you should get the same answer. And that's important to know, so I'm going to put that in a box. It's a broken box, but okay. And so the claim that I want to make is that there's a converse of sorts. This is actually basically all we need to check. Okay, so sorry. What's going on? Okay. Okay, so conversely, so I'm going to put here a condition, and my equals nx, then f is a gradient field. So what's the condition that I need to put here? Well, we'll see a more precise version of that next week. But for now, let's just say if our vector field is defined and differentiable everywhere in the plane. Okay, so we need actually a vector field that's well defined everywhere. You're not allowed to have somehow places where it's not well defined. Otherwise, actually, you have a counterexample on your problem set this week. If you look at the last problem on the problem set this week, it gives you a vector field that satisfies this condition everywhere where it's defined, but actually there's a point where it's not defined, and that causes it actually to somehow, I mean, everything that I'm going to say today breaks down for that example because of that. So, I mean, we'll shed more light on this a bit later with the notion of simply connected regions and so on. But for now, let's just say if it's defined everywhere and satisfies this criterion, then it's a gradient field. So if you ignore, I mean, you know, if you ignore that technical condition, being a gradient field means essentially the same thing as having this property. So that's what we need to check. Okay, so let's look at an example. Well, one vector field that we've been looking at a lot was minus yi plus xj. Remember, that was the vector field that looked like rotation at unit speed. Okay, so I think last time we already decided that this guy should not be allowed to be a gradient field and should not be conservative, because if we integrate on the unit circle, then we'll get a positive answer. But let's check that indeed it fails our test. So, well, let's call this guy m. Let's call this guy n. Then if you look at partial m, partial y, well, that's going to be negative 1. If you take partial n, partial x, that's going to be 1, and these are not the same. So, indeed, this is not a gradient field. Okay, any questions about that? Yes? Mm-hmm.
That condition is only satisfied in certain areas of the function. In those areas, does the function have the properties?
Okay, so your question is, if I have that property m sub y equals n sub x only in a certain domain, in a certain part of a plane, for some values of x and y, can I conclude these things? And you know that it's a gradient field in that part of the plane and conservative and so on. So the answer for now is in general no. And when we spend a bit more time on it, actually maybe I should move that up. Maybe we'll talk about it then, you know, later this week instead of when I planned. But so there's a notion of what it means for a region to be without holes. And basically, if you have that kind of property in a region that doesn't have any holes inside it, then things will work. The problem comes from your vector field satisfying this criterion in a region that has a hole in it. Because then what you don't know is whether your potential is actually well-defined and takes the same value when you move all around the hole. It might come back to take a different value. If you look carefully and think hard about the example on the problem set, that's exactly what happens there. Anyway, I mean, again, I will say more about that later. But so for now, we basically need our function to be. I mean, so I should still say, if you have this property for a vector field that's not quite defined everywhere, you're more than welcome. You should probably still try to look for a potential using the methods that we'll see, but something might go wrong later. You might end up with a potential that's not well defined. Okay, let's do another example. So let's say that I give you this vector field. And the question is, so this A here is a number. The question is, for which value of A is this going to be possibly a gradient? So if you have your flashcards, then that's a good time to use them to vote, assuming that the number is small enough to be made with. Okay, so let's try to think about it. So we want to call this guy M, we want to call that guy N, and we want to test M sub y versus N sub x. Okay, I don't see anyone. Oh, yeah. Okay, I see people doing it with their hands, and that works very well. Well, okay. So the question is, sorry, for which value of A is this a gradient? Yeah, okay, so I see various people with the correct answer. And yes, okay. That's a strange answer on the, but yeah, I see. Okay, that's a good answer. Okay, so the vote seems to be for A equals 8. And let's see. Well, if I take M sub y, that is going to be just AX. And N sub x, that is 8x, so I would like A equals 8. By the way, so when you set these two equal to each other, they really have to be equal everywhere, right? So you don't want to somehow solve for x or anything like that. You just want these expressions in terms of x and y to be the same quantities. I mean, you can't say, well, if x equals 0, they're always equal. Yeah, that's true, but that's not what we're asking. Okay. So now we come to the next stage of, the next logical question. Let's say that we've passed the test. So we've put A equals 8 in here. So now it should be a potential. Sorry, it should be a gradient field. The question is, how do we find the potential? Okay, so that becomes 8 from now on. The question is, how do we find the function which has this as gradient? So one option is to try to guess. And actually, quite often, you will succeed that way. But that's not a valid method on next week's test. So we're going to see two different systematic methods. And you should be using one of these because, well, guessing doesn't always work. And actually, I can come up with examples where if you try to guess, you will surely fail. I can come up with trick ones, but I don't want to put that on the test, but still. So, okay, so the next stage is finding the potential. And let me just emphasize, we can only do that if, step one was successful. If we don't have, if we have a vector field that cannot possibly be a gradient, then we shouldn't try to look for a potential. It's kind of obvious, but it's probably worth pointing out. So there's two methods. And the first method that we'll see is by computing line integrals. So let's see how that works. So let's say that, I take some path that starts at the origin, or actually anywhere you want, but let's take the origin. That's my favorite point. And let's go to a point with coordinates, say, x1, y1. Okay, and let's take my favorite curve, and let's compute the line integral of that field along, the work done along the curve. Well, by the fundamental theorem, that should be equal to the value of the potential at the endpoint minus the value at the origin. Okay. Well, so that means I can actually write f of x1, y1 equals, bless you, equals that line integral plus the value at the origin, and that's just, a constant. We don't know what it is, and actually we can choose what it is, because if you have a potential, say that you have some potential function, and let's say that you add 1 to it, it's still a potential function. Adding 1 doesn't change the gradient. You can even add 18 or any number that you want. So this is just going to be an integration constant. It's the same thing as in one-variable calculus. When you take the antiderivative of a function, it's only defined up to adding a constant. So we have this integration constant, but apart from that, we know that we should be able to get our potential from this. And this we can compute using the definition of a line integral, because we know, well, we don't know what little f is, but we know what the vector field is. So we can compute that. Well, of course, to do the calculation, we probably don't want to use this kind of path. I mean, if that's your favorite path, then that's fine, but it's not very easy to compute the line integral along this, especially since I didn't tell you what the definition is. So, there's easier favorite paths to have. For example, you can go on a straight line from the origin to that point. That would be slightly easier. But in fact, there's even easier. The easiest of all, probably, is to just go first along the x-axis to x1, 0, and then go up parallel to the y-axis. Why is that easy? Well, that's because when we do the line integral, it becomes m dx plus n dy, and then on each of these pieces, 1/2 just goes away because x or y is constant. So let's try to use that method on our example. So okay, so let's say that I'm going to integrate, sorry, oh, how did I end up with 2 yellow? Okay, so let's say that I want to go along this path from the origin, first along the x-axis to x1, 0, then vertically to x1, y1. And so I want to compute the line integral along that curve. So let's say I want to do it for this vector field. Okay, I want to find the potential for this vector field. So here, okay, let me copy it because I'll have to erase at some point. So it's 4x squared plus 8xy and 3y squared plus 4x squared. So that will become the integral of 4x squared plus 8xy dx plus 3y squared plus 4x squared dy. Now, to evaluate on this broken line, I will, of course, evaluate separately on each of the two segments. So I'll start with this segment that I will call C1, and then I will do this one that I call C2. So on C1, how do I evaluate my integral? Well, if I'm on C1, then x varies from 0 to x1. Well, actually, I don't know if x1 is positive or not, so I shouldn't write this. I really should say just x goes from 0 to x1. And what about y? Y is just 0. So I will set y equals 0 and also dy equals 0. So I get that the line integral on C1, well, a lot of stuff goes away, right? So the entire second term with dy goes away because dy is 0. And in the first term, 8xy goes away because y is 0 as well. So I just have the integral of 4x squared dx from 0 to x1. So by the way, now you see why I've been using x1 and y1 for my point and not just x and y. It's to avoid confusion. You know, I'm using x and y as my integration variables and x1 and y1 as constants that are representing the endpoint of my path. Okay, and so if I integrate this, I should get 4/3 x1 cubed. Okay, so that's the first part. And next I need to do the second segment. So if I'm on C2, so y goes from 0 to y1. And what about x? Yeah, x is constant equal to x1. So dx becomes just 0. It's a constant. So if I take the line integral on C2, oops, 2 goes here, I have the dr, then I will get the integral from 0 to y1 of, so the entire first term with dx goes away, and then I have 3y squared plus 4, well, x is x1 squared dy. Okay, so that integrates to y cubed plus 4x1 squared y from 0 to y1, or if you prefer, that's y1 cubed plus 4x1 squared y1. Okay, so now that we have done both of them, we can just add them together, and that will give us the formula for the potential. Okay, so f of x1 and y1 is 4/3 x1 cubed plus y1 cubed plus 4x1 squared y1 plus a constant. Okay, that constant is just the integration constant that we had from the beginning. Or, you know, now you can drop the subscripts if you prefer. You can just say f is 4/3 x cubed plus y cubed plus 4x squared y plus constant. Okay, and you can check if you take the gradient of this, then you should get again this vector field over there. Okay, any questions about this method? Yes?
Is it wrong if you don't include the constant?
No, well, it depends whether you're just trying to find one potential or if you're trying to find all the possible potentials. If a problem just says find a potential, then you don't have to include the constant. You know, this guy without the constant is a valid potential. Just you have others. You know, so if your neighbor comes to you and says, oh, your answer must be wrong, I got this plus 18, well, you know, both answers are correct. Okay, by the way, So instead of going first along the x-axis, then vertically, you could do it the other way around, of course. Start along the y-axis, then horizontally. And that's the same level of difficulty. You just exchange the roles of x and y. In some cases, it's actually even making more sense maybe to go radially straight out from the origin to your endpoint. But usually, this setting is easier just because, see, each of these two guys was actually very easy to compute. But somehow, maybe if you suspect that polar coordinates will be involved somehow in the answer, then maybe it makes sense to choose different paths. Maybe a straight line is better. Okay. So now we have another method to look at, which is using antiderivatives. Okay, so the goal is the same, still to find the potential function. And you see that finding the potential is really the multivariable analog of finding the antiderivative in one variable. So, here we did it basically by hand by computing the integral. The other thing you could try to say is, wait, I already know how to take antiderivatives. Let's use that instead of computing integrals. And it works, but you have to be careful about how you do it. So let's see how that works. Okay, so let's still do it with the same example. So we want to solve the equations. We want a function such that f sub x is 4x squared plus 8xy, and f sub y is 3y squared plus 4x squared. So let's just look at one of these at a time. If we look at this one, well, we know how to solve this because it's just telling us we have to integrate this with respect to x. Okay? Well, let's call them 1 and 2 because I will have to refer to them again. So let's start with equation 1. And let's integrate with respect to x. Well, it tells us that f should be, okay, so what do I get when I integrate this with respect to x? I get 4/3 x cubed plus, when I integrate 8xy, y is just a constant, so I will get 4x squared y. And that's not quite the end to it, okay, because there's an integration constant. And here, when I say there's an integration constant, it just means the extra term does not depend on x. That's what it means to be a constant in this setting. But maybe my constant still depends on y, so it's not actually a true constant. A constant that depends on y is not really a constant, it's actually a function of y. Okay, so the good news that we have is that this function no longer depends on x, so it should be, we've made some progress. We've got part of the answer, and we've simplified the problem. So if we have anything that looks like this, it will satisfy the first condition. So now we need to look at the second condition. Okay, so we want f sub y to be that. And, well, but we know what f is. So let's compute f sub y from this. Okay, so from this, I get that f sub y, so what do I get if I differentiate this with respect to y? Well, I get 0 plus 4x squared plus the derivative of g. So I would like to match this with what I had. So if I match this with equation 2, then that will tell me what the derivative of g should be. Okay, so if we compare the two things there, we get 4x squared plus g prime of y should be equal to 3y squared plus 4x squared. And of course, the 4x squares go away. That tells you g prime is 3y squared. And that integrates to y cubed plus constant. Now, this time, the constant is a true constant, okay, because g did not depend on anything other than y, and the constant does not depend on y, so it's a real constant now. So now we just plug this back into this guy, let's call him star. If we plug this into star, we get f equals 4/3 x cubed plus 4 x squared y plus y cubed plus constant. And I mean, of course, again, now this constant is optional. So you see, the advantage of this method is you don't have to write any integrals. The small drawback is you have to follow this procedure carefully. So by the way, one common pitfall, it's tempting. So after you've done this, what's very tempting is to just say, oh, well, let's do the same with this guy. Let's integrate this with respect to y. You'll get another expression for f up to a constant that depends on x. And then let's match them. Well, the difficulty is matching is actually quite tricky because you don't know in advance whether there will be the same expression. It could be that I got, you could say, oh, let's just take the terms that are here and missing there and combine, the terms that are, take all the terms that appear in either one. That's actually not a good way to do it because if I put sufficiently complicated trig functions in there, then you might not be able to see that two terms are the same. To take an easy one, let's say that here I have 1 plus tangent square, and here I have a cotangent square. I have secant square. Then, you might not actually notice that there's a difference. But there's no difference, sorry. Well, whatever. Okay, so anyway, so I'm saying, do it this way, don't do it any other way, because there's a risk of making a mistake otherwise. I mean, on the other hand, of course, you could start with integrating with respect to y, and then differentiate and match with the derivative with respect to x. But, so what I'm saying is just, take one of them, integrate, get an answer that involves a function of the other variable, then differentiate that answer and compare, and see what you get. By the way, yeah, so here, of course, after we simplified, there were only y's here. There were no x's. And that's kind of good news. I mean, if you had an x here in this expression, that would have told you that something is going wrong. Right? G is a function of y only. So if you get an x here, maybe you want to go back and check whether it is really a gradient field. Yes?
Does this work with functions of more than 2 variables?
Yes, this will work with functions of more than 2 variables. So both methods work with more than 2 variables. So we're going to see it in the case where more than 2 means 3. We're going to see that in 2 or 3 weeks from now. I mean, basically, starting at the end of next week, we're going to do triple integrals, line integrals in space, and so on. So the format is first we do everything in 2 variables, so then we'll do it in 3 variables. And what happens with more than 3 will be left to your imagination. Okay, any other questions about either of these methods? Okay, a quick poll. Who prefers the first method? Who prefers the second method? Wow. Okay. So, well, anyway, I mean, you get to use whichever one you want. And I would agree with you that the second method is slightly more effective in that you're writing less stuff. You don't have to, set up all these line integrals for nothing. On the other hand, it does require a little bit more of attention. Okay. So, well, let's move on a bit. well, let me start by actually doing a small recap. So we said we have various notions. One is to say that a vector field is a gradient in a certain region of a plane. And we have another notion which is being conservative, which says that the integral, the line integral is 0 along any closed curve. So actually, let me introduce a new piece of notation. So just to remind ourselves that we are doing it along a closed curve, very often we put just a circle through the integral to tell us, well, this is a curve that closes on itself. It ends where it started. I mean, it doesn't change anything concerning the definition or how you compute it or anything. It just reminds you that you're doing it on a closed curve. It's actually useful for various physical applications, and also, when you state theorems in that way, it reminds you, oh, I need to be on a closed curve to do it. And so we've said these two things are equivalent. And now we have a third thing, which is n sub x equals m sub y at every point. So just to summarize the discussion, we've said if we have a gradient field, then we have this. And the converse is true in suitable regions. So we have the converse if f is defined in the entire plane. Or, as we'll see soon, in a simply connected region. Okay, I guess some of you can't see what I'm writing here, but it doesn't matter because you're not officially supposed to know it yet. That will be next week. Okay, anyway, so I said the fact that nx equals my implies we have a gradient field is only if the vector field is defined in the entire plane or in a region that's called simply connected. And more about that later. So now let me just introduce a quantity that probably a lot of you have heard about in physics that measures precisely failure to be conservative. So that's called the curl of a vector field. Okay, so for definition, we say that the curl of f is the quantity n sub x minus m sub y. Okay, so it's just repackaging the information we had, but in a way that's a single quantity. Okay, so in this new language, the conditions that we have, the condition that we had over there, this condition says curl f equals 0. That's the new version of nx equals my. Okay, so it measures failure of a vector field to be conservative. So I should probably so the test for conservativeness is that the curl of f should be 0. So I should probably tell you a little bit about what the curl is, what it measures, what it does, because that's something that's probably useful. It's a very strange quantity, right, if you put it in that form. I mean, yes?
Is this one the same as the physics one, or is this the opposite?
I think it's the same as the physics one. But I haven't checked the physics textbook recently, but I believe it's the same. Yes, I think it's the same as the physics one. It's not the opposite this time. Of course, in physics, maybe you've seen actually curl in space, and we're going to see curl in space in 2 or 3 weeks. But yes?
So do you only use this test if the function is defined at every point?
Yes, well, you can also use it. So if you fail this test, then you know for sure that you're not a gradient field. So you might as well do that. If you satisfy the test, but you're not defined everywhere, then there's still a bit of ambiguity. And you don't know for sure. Okay. Okay, so let's try to see a little bit what the curl measures. So I want to claim that, just to give you some intuition, let's first think about a velocity field. The curl, I claim curl measures the rotation component. Of a motion. So if you want a fancy word, that measures the vorticity of a motion. It tells you how much twisting is taking place at a given point. Okay, so for example, if I take a constant vector field, where my fluid is just all moving in the same place, in the same direction, where this is just constants, then of course the curl is 0, because if you take the partials, you get 0. And indeed, that's not what you would call, swirling. I mean, there's no vortex in here. On the other hand, well, okay, now let's do another one where there's still nothing going on. Let's say that I take, the radial vector field, where everything just flows away from the origin. So that's f equals x comma y. Well, if I take the curl, so I have to take partial x of the second component, which is y, minus partial y of the first component, which is x, I will get 0. And indeed, if you think about what's going on here, there's no rotation involved. On the other hand, if you consider our favorite rotation vector field, negative y and x, then its curl is going to be, well, n sub x minus m sub y will be 1 plus 1 equals 2. And that corresponds to the fact that we are rotating. Actually, we're rotating at unit angular speed. So the curl actually measures twice the angular speed of the rotation part of a motion at any given point. So now if you have an actual motion, a more complicated field than these, then no matter where you are, you can think of the motion as a combination of translation effects, maybe dilation effects, maybe rotation effects, possibly other things like that. And what the curl will measure is how intense the rotation effect is at that particular point. Okay, so I'm not going to try to make a much more precise statement. Well, I mean, the precise statement is, what curl measures is really this quantity up there. But the intuition you should have is it measures how much rotation is taking place at any given point. And of course, in a complicated motion, you might have more rotation at some points than at some others, which is why the curl will depend on x and y. It's not just a constant because, how much you rotate depends on where you are. So, if you're looking at actual wind velocities in weather prediction, then the regions with high curl tend to be hurricanes or tornadoes or things like that. They're not very pleasant things. And the sign of the curl tells you whether you're going clockwise or counterclockwise. Okay, so curl measures, well, twice the angular velocity of the rotation component of the velocity field. Now, what about the force field? Because after all, where we got to this was coming from and trying to understand forces and the work they do. So I should tell you what it means for a force. Well, the curl of a force field measures the torque exerted on a test object that you put at any point. So remember, torque is the rotational analog of the force. We had this analogy about velocity versus angular velocity and mass versus moment of inertia. And then in that analogy, a force divided by the mass is what will cause acceleration, which is the derivative of velocity. Torque divided by moment of inertia is what will cause the angular acceleration, namely the derivative of angular velocity. Maybe actually I should write that down. Oops. Okay, so torque divided by moment of inertia is going to be d dt of angular velocity. I leave it up to your physics teachers to decide what letters to use for all these things. That's the analog of force divided by mass equals acceleration, which is d dt of velocity. And so now you see, if the curl of a velocity field measures the angular velocity of its rotation, then, by this analogy, the curl of a force field should measure the torque it exerts on a mass per unit moment of inertia. So concretely, if you imagine that you're putting something in there, if you're in a velocity field, the curl will tell you how fast your guy is spinning at a given time. If you put something that floats, for example, on your fluid, something very light, then it's going to start spinning. And the curl of a velocity field tells you how fast it is spinning at any given time, up to a factor of 2. And the curl of a force field tells you how quickly the angular velocity is going to increase or decrease. Okay, so next time we are going to see Green's theorem, which is actually going to tell us a lot more about curl and failure of conservativeness.